My name is Nigel Ricks. I'm Head of Enabling Technologies within the Knowledge Transfer Network in the UK, and I will be host for today's webinar. As you saw, there was no sound until we had just started, and all participants will be muted throughout the webinar. At the bottom of your screens, you will see a Q&A box. Please use that for submitting questions to the panelists. The chat box, which is also there, if you have any technical problems or general queries or want to introduce yourself to the rest of the delegates, please use the chat box for doing that. And as a reminder, the webinar will be recorded, and the recording and the event materials will be sent to you all in due course. However, please don't now sign off. Do listen to the presenters. So this is the second of a series of 3 webinars being organised by the KTN and by EPoSS. The first one we held was on digital industry last month. Today's is focusing on mobility, and the final one of this series is on healthcare. And we may well extend it at the beginning of next year and look at another 3 topics for it. I would also like to highlight that with webinars, one of the things that we do miss compared to physical events is that you don't get a chance to meet and chat with other delegates. To help people make connections between the delegates of a webinar, we run a facility called Meeting Mojo. The link is actually shown on the screen now, but Natasha will post the link into the chat window so you can all do it. If you pre-registered for it, your account will have been set up and you can go in there. If not, there is a register button when you go into Meeting Mojo. Meeting Mojo allows you to look at the other delegates who've registered. I looked a couple of days ago and there are over 140 people, so I expect many more by now. You can send emails and messages to other delegates to have private chats. It also has the capability of arranging video conferencing, so you can actually request that another delegate has a video conference with you, and the system handles that quite happily. So please do go and look, establish contact and connections, even if you follow them up next week by more conventional systems such as email. So I'd just like to cover today's program. So in the initial 2 presentations, we'll go through the KTN and EPoSS, some background information. Then we will have the 5 main presentations from speakers who have really knowledgeable within this sector, a range of subjects and a very interesting cover of the topics that were important to us. At the end of the presentations, we'll have a panel Q&A. There we will go through the questions in the Q&A window and have one or more of the presenters actually answers. We don't have a Q&A after each presentation, so we can keep control of the time. I will try and schedule a short break just after 11. If we're running over by that point, I may ask everyone to persevere and we'll run straight through. We're trying to finish by 12 o'clock or very soon afterwards. So with that, I would like to introduce Simon Yarwood, who will do the first presentation in terms of introduction to KTN. Simon.
Thanks very much, Nigel. And hopefully Simon will do this before his Wi-Fi collapses again on him, as it has done 4 times already this morning. And I'm going to start, really. So good morning and welcome, everyone. Hopefully you should be able to see my slides. My name is Simon. I work for the Enabling Technologies team at KTN here with Nigel. I have a very short presentation to take you through what the KTN is and what the KTN does. So the short version, I suppose the 1-slide presentation is this. We're here to help innovators create opportunities and partnerships and to accelerate their thinking, really helping people get the best out of the opportunity and get the best out of the idea that they might have. We do this through a series of teams that cover a wide range of topics. This is just some examples. There are many more topics covered by teams in the KTN, and then individuals have their own specialities. So I focus on the use of high performance computing and software optimization and system level energy harvesting. And lots of other people have even more unique interests and specialist topic areas. And it really shows the KTN's breadth of knowledge and our ability to have deep expertise gained through our connections into industry, academia, and the research base. A big thing in what the KTN does, and Nigel's alluded to it already with this excellent program of activities he's been putting on, is around the connections we can help people create through the connections that we have. So here's a couple of examples of some other events we have coming up. So these are knowledge dissemination events, knowledge transfer events like today. And we also work with funding partners in the UK to promote knowledge of upcoming grant funding and contract funding that may be made available to UK companies or companies who operate within the UK. Another aspect of the KTN, which is really important to help inform that deep expertise, is around the communities we have. So that didn't work. There you go. So this is to help people understand in government and people in the KTN to understand what's actually going on in a specific topic area. So it allows us to engage with those multifaceted groups such as academia, research, in industry, and look at topics which posing significant challenges to the UK and globally. And we run, to do this, a series of innovation networks. These are our current open innovation networks. As I've previously run an innovation network on energy harvesting, high performance compute software, energy efficient optimization of software for compute. So we cover a wide range of topics, and these typically run for a year, 2 years, a defined period of time with a specific goal in mind to try and get some learning and understanding and help further the community itself. How people can get hold of all this information in future? Well, there are emails that you can subscribe to from the KTN website. The KTN website itself also has information. Its URL is at the bottom of my end slide. But really, you can tap into updates on events and updates on funding and subscribe to newsletters from various different areas of the KTN. And that actually already brings me to my last slide. That's my contact details. Please feel free to drop me a line if there's anything you'd like to talk about in regards to developing a new innovation. Thanks very much, Nigel.
Thank you, Simon, and pleased that your internet held out. Elizabeth, would you like to give us a quick overview of EPoSS? And you are on mute at the moment.
Good morning, everybody. So it's my pleasure to introduce EPoSS to you as a co-organizer of this meeting. Let me just share my slides with you. So here we go.
That's perfect.
Okay. So my name is Elisabeth Steinmetz. I'm EPoSS Office Director, and it's my pleasure to introduce the European Technology Platform on Smart Systems Integration, the co-organizer of this event, to you today. Should move to the next one, but doesn't. Okay. So what is EPoSS? EPoSS is an industry-driven policy initiative. And we are collecting the R&D and innovation needs of our members and defining based on that policy requirements. So this is at least one of the goals that we have. And all what we do is related to smart systems integration and to integrated micro nano systems. And now more and more, of course, implementing artificial intelligence into these smart systems. Here you can see the current list of EPoSS members. So we are representing European Smart Systems community, large, medium-sized, small entities all over Europe, and RTOs as well, of course. And in EPoSS, we are hosting several working groups, one on transport, one of the biggest ones that we have, so on health, on energy, on digital industry, on agri-food, so on all the typical smart systems applications that companies are running in Europe. And new is that we, together with the help of Nigel, started to have a group on AI at the edge, meeting now and preparing the first documents to be published hopefully still this year. I think I do not have to talk about what a smart system is, and just to show you some of the typical examples of EPoSS members here on this slide, coming from industry, industrial applications, medical, automotive, and environment. I think what is maybe more interesting is what can EPoSS bring to it, and what are we doing there. So we try to really connect the experts and create common European approaches for research and from research to production. And so based on that, we are defining research priorities. We are very active in creating roadmaps and SRAs. So this year, EPoSS is heading the ECS SRA, the Electronic Components and Systems roadmap. We are involved in the roadmaps of other public-private partnerships for the upcoming new Horizon programs like CCAM, like Towards Zero. So my colleague Gerion will talk about that in detail a bit later. So we are defining strategic innovation processes and roadmaps. And last but not least, we try to mobilize public and private financial resources to do all this. Currently, we are involved in Horizon Europe. Of course, we have published papers to position SMEs in this context. We are now integrating with Euripides, the Euripides community, into EPoSS for upcoming Eureka programs, and we are deeply involved in the Excel joint undertaking. So the succeeding program will be the Key Digital Technologies public-private partnership, which is currently under preparation and will hopefully start towards the end of 2021. Besides that, as I said already, we are involved in Towards Zero and CCAM, and quite new is our involvement in the ESTER Alliance. So this is in the area of health applications. So this is more or less a quick overview about what EPoSS is doing. And if you want to join us, please get into touch with me or through the EPoSS website. And we are very open and looking forward to new members, of course. So thank you very much for your attention so far. And yeah, I'm looking forward to the presentations from the experts now.
Thank you very much, Elizabeth. And yes, the work of EPoSS is very good and produces excellent roadmaps. So people from the UK, I would recommend that you go and have a look at the ECS, etc. I'd now like to hand over to Gerion for the first of the presentations. When posing a question through the Q&A window, if you could add the name of the presenter at the start of the question, it will help us remember who was due down to answer it. So I'd like to hand over. Gerion, that looks fine, but you are on mute. And you are still on mute.
There we go.
There you go. Take care.
Nigel, thank you very much for the invitation, and it's my pleasure to tell a little bit about this topic here, smart systems for the automobile and the mobility system of the future. By doing that, I'm also, in a sense, reporting about what Elizabeth already announced, that there is a working group in EPoSS that we once was called the Automotive Working Group, that turned into the Transportation Working Group recently, and that I have had the pleasure to coordinate a little bit since about 12 years. And we've gone through processes of promoting like the electrification, the automation of road transportation, for example, from the perspective of the EPoSS community in the last few years here. And yeah, that's quite a story, and I'd like to show you a few of the highlights and also try to make a little bit of a link to artificial intelligence, of course. When we had the chance to ask people recently what they're expecting from a future transportation and mobility system. The answers were quite diverse. And interestingly, the topic of mobility is something where pretty much everybody is an expert. And this gives us great opportunities of trying to find out what people really expect and what really people wish to have for the future. There's three big paths that you see being mentioned there in most of the answers and responses then. And you see them here on the slides. It's about, of course, having a sustainable system that does not have too much of an effect on the world climate, for example, and the environment. They are dreaming of seamless systems, of course, that are convenient to use. And they're also referring to the topic of inclusiveness all the time, because in the end of the day, we all will be needing once in our life systems that are convenient and that are meeting our maybe even special requirements. And this is also like a common expectation in the community. I believe this is also the point that would probably be modified a little bit or could take into account expectations related to like the COVID-19 situations, that is putting people's expectations a little bit more even in the center of planning for future mobility. In the EPoSS community, we have recognized that smart systems permit and enable the transformation of the mobility system without such vision since long time, because they are key to enable green, integrated, interoperable mobility solutions. They facilitate taking into account the human in the approaches, and they support transportation, the transformation of transportation as a whole with technology transfer from auto into other domains. And you see this little icon here on the top right, which we have taken from our strategic research agenda, with the smart system in the center. And if you consider all these roles that smart systems shall play, it's clear it is not sufficient to just consider sensing and actuation as the key functionalities. You also need to consider cognitive capabilities and linking the system into greater networks and bases of knowledge. And therefore, connectivity is playing an important role as well. From the perspective of the EPoSS community, we can serve all the big trends in future transportation, of course, be that automation, be that alternative powertrains or electrification. You see a little graph here that we once created where we saw, even if whether we talk about green vehicles or connected and automated driving, not just at the level of the applications there is synergies, but also in the bottom when it comes to sensing, perception, prediction, decision, controlling and acting. There indeed, a lot of similarities can be found in the architectures, in particular in the questions of making systems reliable, robust, maybe fail operational. Automated driving, I think, is a very good example of where you see the role of smart systems as enabling technology, and also as an enabling technology that can support a paradigm shift. Originally, we have developed that topic out of advanced driver assistance systems, assuming that there's more and more functions that the vehicle systems can perceive based on sensing, based on the sensor data fusion. And at the latest of that, a driver can, for a short time, take the hands off the wheel and the roads and the eyes of the road, and have the vehicle drive for a while till it comes to a point where it needs human support. But the interesting step is, of course, if you take the driver completely out and make the system self-driving, driverless. For that, there's more than just what the capabilities of a smart system in the vehicle can deliver. The need actually the embedding into greater data availability and knowledge sets. And this is also the point where artificial intelligence is coming in. Just to show you one example that I find the most striking one, that is the situation on the road. You have a person close to a crosswalk and you have a super intelligent smart car approaching, the question here is not just what the car can perceive and what it can detect and maybe a 3D image, but the question is of what this means and what expectation the car system has of that situation. The crucial question here is whether that person will cross or will not. Because in the one case, the car, of course, needs to stop and the other can continue driving. And of course, we want to avoid a car stopping all the time if there's just the slightest possibility of somebody maybe approaching the road, but rather we try to be able to tell in a trustful way what will happen, to understand the intentions of the road user. And here, indeed, the capabilities of smart systems themselves are quite limited. And we need to have additional information. We need to understand patterns. We need to know and take into account a big set of experiences. And that's where, from my perception, artificial intelligence will play a crucial role. Will help smart systems to gain trust in such situations in traffic. And you can imagine a lot of other situations on the road where the same will happen because we are having an interaction between the technical system and the human system. Going a little bit further, urban air mobility is another exciting field where smart systems pave the way to make that happen, particularly because we are making use and we're transferring experiences and knowledge from the car into the third dimension, whether that's electrified powertrains or whether that's automated control of systems. And again, this needs AI for the same reason. Maybe that's a bit also the role here of the EPoSS community to point to these needs and to show where the future directions are in. This has been well reflected in a lot of roadmaps and documents that were published in recent years, whether that's on the electrification of road transport, on automated driving, but also in our strong support to the European Commission in drafting the Strategic Transport Research and Innovation Agenda, the electrification of the transport system, the automation and connectivity. One important aspect here is that, of course, the EPoSS community and their members just in very little cases are developing technology that you can directly put on the road. We are actually part of an ecosystem of enablers, which you see down here on the bottom, that is in interaction with an ecosystem of applications that needs to understand where are the technology pushes that we can define, and also what is actually the technology to be pulled according to user expectations from the application domain. And I think that's a very exciting interaction, which also the EPoSS community is very much supporting through the lighthousemobility.e of the Excel joint undertaking. Talking about Horizon Europe, because that's a very hot topic for the time being, of course. And currently we are trying to shape some of the discussions about future partnerships here. And Elisabeth already mentioned these three ingredients that you see here on the right side. So the KDT, which is the successor of the Excel joint undertaking, looking into all the building blocks of future applications, not just in mobility, but in many other application fields too. And then you see on the right side, on the one hand, the CCAM partnership that's looking into automated driving, and the 2.0 partnership for the zero emission road transport. Very clearly, while the building blocks are provided by KDT, the applications into the vehicle, into the domain of something you can put on the road is in the other two partnerships. So there's very close interaction, and we are happy to say that the smart systems community is facilitating this integration into the future planning. Just two more slides, one on CCAM very shortly, connected corporate automated mobility with the objective of leadership in safe and sustainable road transport through automation. Here in the clusters 5 and 2 that you see in the big circle in the middle, these are the ones that very closely emphasize the need of further innovations in technology. And number 5 particular is mentioning smart systems in it. Number 2 is particularly related to smart systems too, and number 5 also includes AI, by the way. And I think we took us quite some effort to always make sure that the community is aware of the fact that smart systems and AI are essential for the safety of connected and automated driving. If we would not have progress here, we needn't talk about validation or the integration to the transport system or any further demonstrations. The other 2.0 towards zero emission road transport very clearly again has a strong focus on vehicle technologies here. The link is, for example, through power electronics, but all the questions of energy efficiency of electrified vehicles using green energy, of course, will be supported not just by smart systems, but also by knowing how to use the energy in the most efficient way and making use of the knowledge we can gain through AI. Thank you, Nigel.
Thank you very much. And that's a great start for an overview for today's presentations. What I'm going to do now is ask Cyprian to take us into some of the technical details, and particularly looking at some of this detection that will be required as we go through connected autonomous vehicles. That looks fine, but you are still on mute.
That's also fine because I haven't said anything yet. Okay, yeah, let me welcome to my presentation, and thank you for the introduction. We'll talk about the spiking AI, and raising the question if the AI at the edge is have to be a spiking AI, means a neuromorphic implementation of it. Specifically addressing this topic by looking at monitoring and signal processing in radar to make it a little bit more concrete. And therefore, it's also one thing to start with giving the context. We saw already, 1 second, let me see. Yeah, this way. Okay. Just to motivate in the first place what kind of problem we are facing, and giving more concrete numbers to this also, that you have a better picture of what dimension the problem is. We already saw the levels which were mentioned by Geron in his talk. We have this level 1 to 5 for the advanced driver assistance systems and autonomous driving. While we today see more or less in a mass market the level 1 and some already level 2. And one strong driver is here, which is probably not that known to most of the people, is the new car assessment program, Euro NCAP, which is, you know this probably, well, looking for new cars. This is the 5-star rating, which is always advertised that the car is quite safe. And there's an increasing requirements to the scenarios you need to be able to satisfy. And this is, for example, now for 5-star rating of 2022. Looking forward, you need to fulfill corner scenarios, so intersection scenarios, and therefore you need more sensor equipment on your car. Usually this would end up in corner radars to be able to sense in an intersection scenario better. And here you see already with the moving from level 1 to level 2, you have an increased number of sensors around the car. And if we now looking further to what comes next, we are seeing that for level 3 and especially then level 4 and 5, when it is about autonomous driving, we see that there are a bunch of sensors which need to be added to the car. especially when you want to run the car autonomously. You need a 360-degree coverage of your sensing equipment, and this in a redundant fashion. That means LiDAR, camera, and radar, and all that need to be fused. So as a consequence, it is quite clear that at the end you end up with a humongous flow of data and a high demand on compute performance to cope with this object classification, detection and classification in these complex scenarios on this high data stream. And the the target and the need which we have here is to reduce the amount of data intelligently in every part of this chain of processing we have then in such a complex environment, and find an energy efficient way to do the computations. And to bother you even more with numbers, I want to dig a little bit deeper now also into the radar aspect, and show you what that means. So if you look at today's radar sensor, which is a so-called FMCW system, frequency modulated continuous wave radar. And here showing it's a simple example in automatic cruise control sensor. When you look at the early versions, you basically have more or less a sensor which is processing all the stuff until the drive command. That means it gives you acceleration, deceleration commands out of the sensed situation, and the objects which are classified if you have an obstacle or a preceding car which is slower and you have to slow down, or is accelerating and you can accelerate again. So if we look at such a system, so a radar sensor, we just pick a system which you would see today deployed in cars today. We're talking about, let's say, 3 transmitter channel and 4 receiver channel radar device. And when we look at the so-called MMIC, monolithic millimeter wave integrated circuit, you see that with 4 receive channels, we will end up in a max of 400 megabit per second per channel, which ends up to be 1.6 gigabit per second data stream, which is coming out of that one sensor. Yeah? And that would be fully sufficient to do something like an automatic cruise control. When you look at the processing of that, you create in radar range Doppler maps, and here there's no reduction in the data stream. Then you detect where are objects in means of stronger reflections, and you look where they come from. This is direction of arrival computation. And doing that, you can reduce the amount of data up to 5 to 50 megabit per second, about, yeah, just to give a ballpark here. And with these reflections, which you selected then to be significant, you run an object clustering and classification to end up in an object list, where and this object list usually contains then information about here there's a car, a pedestrian, a bicyclist, or whatever in this distance with that speed and so on. And here you see already that you end up with 0.08 to 0.8 megabit per second, again as a ballpark. Yeah? And if you then take the decision, so the system takes the decision on acceleration, deceleration, for example, this few bits per second. Looks quite okay if you look then on the data stream, because you can cope with this in a very early stage. But if we're now looking forward to the different levels, 1 to 5, We already see that moving from 1 to 2, you're rather not dealing with a drive command, but you're looking for the object list for the combination. This is actually today the regular output which you deal with. So you have a higher data rate which you need to cope with, but it's not that much. When we look towards moving to level 2 and 3, there's a strong tendency and actually effectively a need when you want to fuse with a similar representation on a similar representation with camera and LiDAR, that you have to look at least at the detections. So that means the strong reflections which you selected out of the range Doppler matrix from a radar processing. And as a matter of fact, you have then from one sensor already a higher data rate which you have to cope with. So we see moving to higher automation levels, we even end up with a higher data rate to be processed. And that makes the situation certainly more worse. If we now looking to solutions to this, as I said, we need some intelligent way to deal with this. And we have some parts in this processing stages here at the end. Everybody would agree, object classification and so on. This is a classical domain for neural networks, kind of AI approaches. But you also might consider this in earlier stages of the processing and also the monitoring of the devices for functional safety. So if we want and to give a more clearer picture also, or an estimate of what we're talking about in total, David Patterson gave at the Design Automation Conference once an estimate here. We are today dealing with level 3 capable systems with around 350 watts of computational power, so to feed the computational engine. And it is expected to go up to 1000 watts in level 4 and 5, which means if you look at electrical cars, definitely will have a substantial impact onto the range of these cars. And one corridor to address this, or solution corridor to address this, would be neuromorphic implementations of the artificial intelligence components in the system, and certainly consider to apply artificial intelligence with this way of implementation to more stages of the overall processing, including the monitoring and functional safety aspects of such systems. The reason for this is, and what is the motivation for this is, here was already given in 1997 by Professor Maas, where he proved in its paper that the computational complexity which can be covered by spiking neural networks is substantially higher than with classical artificial neural networks. And there was here also an assessment on different applications by a startup, which shows that, exemplifies that with neuromorphic spiking neural networks, you might be able to address these performance needs with much lower power consumption. I, by intention, use the term "might" in this circumstance because, as you see, the advantage or the capabilities were already proven in 1997. We have now 2020, and you can guess yourself, looking around, how many solutions you see already with spiking neural networks, how much this is already deployed. So there's a lot ahead of us to make this happen effectively. We are happy to get support by national funding for this, and this is the KI-ESIC project funded by the BMBF. And here we're looking at the signal processing, which I showed you, to be addressed with spiking neural networks, and to see if we can leverage this power advantage these networks supposed to have. And going forward, again, the reason is that the information is encoded in spikes, and we have lower power consumption because these networks are generally less active. So we have few spikes which are sparse, so it's a sparse coding, and it's the asynchronous activity which you have in these networks. Here's an example for one publication which shows that these networks accomplish the same pattern recognition task with much less energy. So there are also proofs out there for concrete implementations. But what one should not forget about is that, as we haven't seen so far, industrial solutions with which proved in product the application of these kind of solutions with substantially reduced power, because otherwise you would see a lot of
at the moment you're
solutions.
frozen. Okay.
Huh? Yeah. Okay. But
the webinar froze, the slides froze, and your voice wasn't there. But do carry on. Let's see how it goes on.
Okay. Yeah. So as I said, you don't see so many solutions yet out there. So there's a lot of work ahead to leverage these benefits, which are obviously there, but it strongly depends also on the area where you apply it, because it requires some quite individual approaches to make this benefit happening on your concrete solution, let's say for the radar processing in this case. Moreover, it's quite important to look at additional benefits which these networks can provide. I said they are asynchronously active, and they have a low activity. So especially radar is one of these solutions where you have sensitive RF circuits, which might be disturbed by this activity of monitoring, especially if you do this digitally. The very standard situation for the sensitive circuits is today having the digital activity in the areas where you have usually no RF activities. With these spiking neural networks, you have the chance to run continuous monitoring of the device without a disturbance or much lower disturbance. So leveraging all the benefits of these kind of networks. So as a conclusion, I hope I gave a lot of motivations that this AI is not only attractive, but also necessary to deal with these complex autonomous driving challenges, and that neuromorphic solutions with their promise of a lower power consumption and potential lower disturbance of these sensitive systems are a path to cope with this problem. We have mainly the challenges ahead. That means have a functional safety to fulfill the functional safety requirements using artificial intelligence approaches, because this is rather tricky. But on the other hand, we also have the opportunity to use AI, especially to fulfill the functional safety requirements, which is somehow sounds like making the fox in charge of the hen house, but effectively is an opportunity which probably has to be looked at more closer. And therefore, it's quite essential to invent SNN solutions for functional safe AI to be able to fulfill all these promises which we put out for autonomous driving. Okay, so that would be from my side. Yeah, questions are coming later, as I think was agreed. Yeah.
Hello, everyone. So I'm Nigel now, because his internet connection has just dropped out. So thank you very much, Cyprian, for the presentation. I believe our next speaker is Radu. So I'm going to pass over to Radu now. And just as a reminder to Cyprian, we'll be doing the Q&A at the end, but if there's anything you think you can answer in text typing in the Q&A box, please feel free. There's a couple of things in there, I think, for you waiting. Thanks very much.
Thank you very much. Thank you very much for inviting me. My name is Radu Grosu. I'm a professor at Technische Universität Vienna, and I'm the head of the Cyber Physical Systems group of the Faculty of Informatics. So I'm going to talk about neural circuit policies enabling auditable autonomy. Our inspiration comes from C. elegans, which is a very small worm, less than 1 millimeter length and 0.01 millimeter width. And being so small, its 302 neurons can communicate with each other without attenuation, without using spiking. We consider that spiking is a very important implementation issue. It's like analog to digital conversion. And it's very important for implementation, but not from the point of view of learning. The nematode has around 8,000 synapses and 95 actuators, which are the body wall muscles. Together, they allow amazing associative learning capabilities and social behavior capabilities for this neuron, for this small and the C. elegans nematode. Like any cell in the body of every organism, a cell has a membrane, and membrane is fat. So as a consequence, it's an insulator. And there is a concentration of ions outside the cell and a concentration of ions inside the cell. And the difference in the concentration of these ions defines a membrane potential, V. Okay, this is, for example, cell I, so it has a membrane potential VI. And since this is an insulator, it acts as a capacitor, so you can write for the membrane of the neuron, you can write the capacitor equation where the rate of change of the membrane potential is the sum of its currents. Now there is a lot going on inside even these small neurons of C. elegans, so we are going to simplify them for the purpose of machine learning by concentrating only on 3 currents: the leaking current that you see here, the synaptic currents, the chemical synapses, and the gap junction currents, which are the electric synapses of the neuron. So what are these currents? So the leakage current is essentially a proportional controller where the error is the difference of potential between the resting potential and the membrane potential, and the proportionality constant is the conductance. Then there is a gap junction current, which is also a proportional controller, where the error is the difference of potential between the 2 neurons, and the proportionality constant is the conductance between the 2 neurons. It's just a small channel that resists to the exchange of ions. But the most important one are the chemical synapses, because this is where learning happens. So how does this happen? So what you have these bubbles filled with neurotransmitters that come through the axon to the synapse. There they bind to the synapse and they open and release neurotransmitters. And these neurotransmitters then go and bind to the receptors of these channels that you see here. And when they bind to the channels, they open them. Okay, so now you can write a very complicated differential equation about what is going on here. But this is actually simplified by assuming that there is a maximum conductance, GSIJ, and then there is a presynaptic potential based conductance. Okay, it varies with the presynaptic membrane potential. And then there is also this, and this is a conductance, and this has to be multiplied with the difference of potential such that you get a current. Now, if the difference of potential is positive, then ions flow inside, so the synapse is activating. And if the difference of potential is negative, then this expresses the fact that ions are flowing outside, like this chlor ion, which is negative, it flows outside. and as a consequence, the synapse is inhibiting. Now, the entire differential equation, behavior, concentration, the concentration of neurotransmitters, the rate of binding to the receptors, and the rate of opening, all of this is captured with a very nice sigmoidal equation, which might be familiar to you from artificial neural networks. So actually, it doesn't happen in the neuron, it happens in the synapse, and it has this nice shape that depends on the presynaptic potential. And mu is actually the threshold, what is called firing threshold, wrongly, because these neurons are not spiking. And so there is no firing going on here. It's just a very smooth function, sigmoidal function. Now, what can you do with this? You can have various policy motives, like, for example, activation, as I was telling you, inhibition. You can have a coupling when you have a gap junction between the two neurons. And the more interesting are the one that corresponds to feedback connection. The connections like the sequencing, where you have activation and inhibition. The conservation. So sequencing means X goes first and then Y goes. Conservation means they behave essentially the same way, is also a way of implementing fault tolerance. And sorry for that. And then you have mutual exclusion or selection. So you see when X goes high, Y goes low. All right, so what can you do with this kind of primitives? Let me give you an example. So suppose you have an expression, theta greater than X. Now, in compilers, you might have learned that you create a abstract syntax tree for it, where you have theta and X as inputs, and then you have a comparator that says greater than or equal. Now, how can you implement this with neurons? So first, you can say theta and X are sensory neurons. Then you have an interneuron which does the comparison. And then you want to do something with it. So you take, for example, the sequencing primitive. So the first neuron activates the second, and that second inhibits the first. So which means that the first neuron is active, and the second neuron would become active when theta is less than X. Okay, when this is this neuron, so to say, is high. Okay, so this can implement a while loop, and within this while loop, you can have an activation of a motor neuron, which says go back. Now you might ask, okay, so what's the big deal? Because we already have this in programming languages. The main idea is that this circuit that you see on the left and you see it on the right as a while loop has parameters that are learned automatically, like the threshold theta and the strength of going back. With what velocity are you going to go back? All right. So using these primitives, you can do design. For example, you can implement a lane keeping controller where you have a camera input stream, and then you have a set of 4 levels of convolutions to extract features from the camera stream. And this serves as our sensory neurons, the 32 features that we get from the convolutional layers. And these sensory neurons are connected then to 12 interneurons. So these 12 interneurons process the sensory information appropriately for the command neurons. Okay, the 6 command neurons, and the command neurons steer then the motor neuron. Now this interconnection between the neurons is learned. Okay, also, so all the synapses and their strengths have to be learned. And but what is nice about this is that we have only 19 neurons explaining the lane keeping. And for example, this one says turn left slightly, turn stronger left, and turn very strong left. And the other ones say turn right, turn stronger right, and turn very strong right. And when all of them are disabled, you go straight. Okay, so now these neurons are connected, for example, left, right, are mutual with other. So if you turn left, no, turn right at this time. Okay, so what can you do with that? Okay, so now sit back and relax, and I hope you can hear. Can you hear my presentation?
Yes, yes, audio is coming through.
All right. All right. now you see our network in action. So the attention map shows you where you are looking. So it focuses to the horizon. You can see the attention map below. The networks are much smaller than the state of the art. So by the way, this is driving in Boston. So the networks are highly robust to environmental perturbations. Like here you see the input actually gets distorted by the rain. And you can see the attention map stays focused, even if the input is noisy. By the way, this is my PhD student, Matthias Lechner, driving in the streets of Boston, actually outside of Boston. So these circuits are called neural circuit policies. So these are new generation of deep models, enable visualization. They are more robust and auditable. So this is joint work with IST, Vienna, and with MIT, and was published in Nature, Machine Intelligence. But it was not only published in Nature, Machine Intelligence, it was also, it made it on the cover of Nature, which was for us very nice. And here you can see the state of the art. Let me start it here. So the controller, 1,100 neurons. So they are in 2 layers. So this is also a convolutional neural network with 2 layers. And now you see the attention map, how it looks like. I mean, it's a mess. I wouldn't like to be driven by such a car because it really concentrates outside. And you're going to see now when it gets to the steep curve, it's going to make an accident. I mean, it's going to get out of the street. It's going to stop for a second and then continue. So this is state-of-the-art end-to-end deep learning for autonomous driving. You can replace a controller with something that is called continuous time recurrent neural networks that you see here. So in this case, you have 64 of them, and they are connected all to all. So it's very, very hard to explain what they are doing. It's almost impossible. And again, here you see when they take the turn, the curve here, they get in trouble, and it went actually out of the street, and then it had to come back. So you see the video stopped for a second. And the most popular recurrent neural networks are the LSTMs, developed, by the way, in Austria by Hochreiter. And here you see, here we have 64 of them. They perform somewhat better. And now you are going to see what happens on the steep curve. So they also get out of the street because they look also too much everywhere. So it's not so clear. It's more difficult to distinguish the road from the outside of the road. So you can see it focuses also on the outside. It focuses mostly on the road itself, but it also looks a lot to what's happening left and right on the outside of the road. All right, so this is what we have done. So similar technology we have used for in this Grand Prix Berlin of autonomous racing. That was this time, in fact, in a simulated environment. And these were my students so obviously we used AI techniques in order to win, in fact, the race. All right, so that's all from my side. Thank you very much again. I'm going to be happy to answer your questions in the Q&A session. All right, so I hope I stopped sharing. Did I?
I think so. Yes.
Right,
Thank you very much. It is interesting to see that developments within this quite technical area come from many different sources, including biology. As we're about okay on time, what I'm going to suggest is people can take a 5-minute break, take a cup of tea, make a cup of coffee, but please be back in 5 minutes and we'll restart with the presentation from Hal. So 5-minute break. Welcome back, everyone. We're going to restart the session now. I'd like to ask Hal for the next presentation.
Everyone, so
Okay.
share my screen. All right, can you all see my screen?
Yes, that's perfect.
Great. So hi everyone, and thank you very much for the opportunity by KTN and EPoSS to present at the AI at the Edge Ability webinar. I'm very honored to be here today, and my name is Hal. I'm a co-founder and CEO of RoboK, and I'm here to present on a topic very close to our heart, that is sensing at the edge, about optimizing AI-based computer vision solutions for low-power embedded systems. So for today's session, I will first start with an introduction on perception, the application of it, and the challenges associated with performance at the edge. And then I will give a few technology demonstrations showcasing examples of embedded intelligence at the edge, and also offer some case studies, including our collaboration with partners and customers, and also talk in general about AI-based perception going forward, about the trade-offs and the opportunities. So perception, it is really about understanding the environment. It is about understanding where you are, what is around you, and what they mean. It is an important building block for autonomous systems, and it can use sensors such as cameras to perceive and measure the environment. Other sensors could include radar, LiDAR, etc. Usually with AI-based software solutions, that could often require powerful computing platforms for real-time performance, and especially for those safety-critical applications. So for advanced perception, some of the application could include unmanned aerial vehicles, autonomous drones, autonomous vehicles, robotics, and as well as use cases in advanced manufacturing, specifically related to Industry 4.0. But the perception system is a combination of hardware and software. And for this kind of different applications, it could often require different level of accuracy and performance. And because there's a trade-off as well, that's on cost and performance, this is especially critical for achieving cost efficiency and competitiveness of the product and solution, especially for a wider adoption. Some of the challenges for at the edge could come within the selection of sensors. So if I take localization application as an example, which is a method and a process of understanding where it is locally and globally, if we look at different sensors, there's a different level of trade-off between cost of sensors, the computational complexity, and the accuracy it is able to achieve. And there's also the underlying advantages and limitation with each kind of sensors. For example, take camera as example, while it is able to provide rich information, it could be limited by lighting conditions, situations such as motion blur, or in textureless area that could all have a detrimental impact on the performance. So in essence, it's really about the trade-offs between the cost of the sensors and performance in trying to use AI-based perception for the specific application. In terms of the computational cost, I think during the sessions, we talk about using sensor fusion that utilizes multiple sensors and their respective strengths and advantages for more robust performance. But that would really mean even more data. With a multimodal sensor fusion approach, it could easily produce terabytes of data each hour. But as mentioned before, real-time processing is especially important for safety-critical applications. And those powerful powerful and complex AI algorithms often require a powerful computing platform, as shown in the picture here, where it is basically a trunk of GPUs in order for the autonomous vehicle to be able to make decisions in real time, robustly and safely. So what I'm really going to talk about is embedded intelligence at the edge. What optimization really means for AI-based perception, it is about design of the efficient deep neural networks and also applying optimization methods to inferencing, such as using quantization, pruning, and also looking at specific hardware architecture and accelerators. The optimization would mean a reduction in the size of the model and also a reduction in the latency. And that is about the amount of time to run an inference instance for a specific model. So instead of processing in the cloud or powerful processing units, it could mean deploying AI-based perception models on single board computers, as an example shown on the right, as an example of a multifunctional perception running at the edge. Let me give a brief introduction to RoboK. We focus on developing embedded intelligence at the edge. And that is about vision-based 3D reconstruction, optimized for low-power embedded systems, and also utilize the camera as the main sensor for optimized detection in both 2D and 3D, localization, tracking, and in particular, depth estimation from 2D images on low-power embedded systems. We are a spin out from the computer lab at Cambridge, and we have been working with customers and partners in applications such as in a digital twin for autonomous emergency braking and other advanced driving functionality, and also as 3D sensing modules for both passenger and commercial vehicles in both retrofit and also for the actual production programs. And also we work with partners in sensor fusion that's utilizing sensors such as cameras and IMU, also working on embedded systems for robust localization for indoor and outdoor applications. In terms of the technology that I'm about to demonstrate, it is about embedded intelligence at the edge. What it means, it's about creating robust 3D perception for low power computing platform. And the main sensor is about using monocular RGB camera that has the benefit of reducing the cost of the sensors and also, therefore, the cost of the systems. We've worked with both real-world data and simulation, and the key benefit and the key vision is about enabling scalable and cost-effective autonomous navigation solution for applications such as cars, robots, and machines cost-effectively. Here are some more demonstration of the vision-based sensing for low-power computing platform. And here on the left is about examples of extracting features for 3D reconstruction directly from 2D images. And on the right, it's a multifunctional model including detection, tracking, lane detection, etc., from 2D images all on embedded systems. We have recently presented our work on localization at the edge at the ARM Developer Summit and presented our discussion on how do we optimize a sensor fusion-based localization, specifically for low power embedded systems for both outdoor and indoor setting. And here, as we actually approached the underground car park, the localization was able to continue based on the vision-based localization method, although GPS becomes unavailable in this instance. And the key component of our technology is about information from 2D images, but still on embedded systems. Here we utilize a self-supervised learning approach to estimate depth for each pixel from just monocular camera images. We have again applied optimization methods such that such a model can deploy on low power embedded systems. When we compare with academic benchmarks, we're able to achieve top ranking accuracy on a public data set compared with other models that would require much more powerful GPUs. Here the demonstration, the warmer the color it is, it means the closer it is to the Eagle vehicle. We've also tested our model on our own data set, as well as customer data set. And here's the demonstration of the point clouds being generated from a monocular depth estimation for each frame. And next, I would like to talk about some of our collaborations with customers and partners and how we deploy those embedded intelligence for applications. In particular, we've been working with Siemens on a digital twin solution for autonomous driving. And here the solution is mainly used for validation and verification. And we have worked with Siemens on providing our 3D reconstruction algorithms in order to demonstrate an autonomous emergency braking function as a starting point in a closed loop digital twin, where a vehicle has been simulated on a physics level, and that's able to range from the ECU to steering system, braking system, as well as the simulation comes from different sensors modes, including camera, radar, etc. We've also presented this work with Siemens and ARM on a partnership that's announced at the CES start of this year, and where we provide the 3D reconstruction and detection algorithms that was running on the ARM-based architecture that's able to generate the critical depth information in real time that provides signals that triggers an autonomous emergency braking function. And this has been demonstrated as part of a digital cockpit demo. Through this collaboration, we've also written articles on how we together built this 3D perception systems that could have a significant benefit in terms of the memory and also the processing footprint that's required. Some of the other collaboration we've had, including for passenger and commercial vehicles for both actually the production program that's looking at testing and validating the technology itself, and also in the retrofit space, utilizing existing sensors that's on specifically commercial vehicles. And the benefit of the solution is it provides scalable and modular perception modules for the customers to able to choose and arrange their architecture. And here are some just demonstrations on the 2D and 3D perception demonstration on the urban roads running on embedded systems and also actually in different geographic locations. So in overall AI-based perception at the edge, what we believe that the trade-off continues and there's still additional opportunities with the technology itself. The biggest trade-off with running AI at the edge, I believe it's also about cost efficiency versus robust perception. Where we adopt a modular approach to autonomous driving, and with perception being a critical and fundamental step for autonomous driving. But this is not where it stops. In order to actually plan path reliably, you need perception to know where it is and act around both dynamic and static agents in the environment, but also about how you plan and according to the situations, as well as taking a human-centered approach to being able to actually gain trust from humans on board as well. There's also about the efficiency of each software component and the cost of each component for both sensors and compute. And all of this can affect the viability and feasibility of autonomous vehicles on the application that's able to apply the technology to. And about deep learning possibilities, inevitably, it has increased the computational complexity, which could actually render some of the applications cost prohibitive. But there's optimization that could be applied that's able to maintain the level of performance as a much more complex model, but it will be able to really implement in a real-time setting through the optimization method. So going forward, we believe that robust perception at the edge can continue to unlock the next generation autonomous solutions, and we're truly honored to be part of this journey. And if you're interested in hearing more about deploying AI-based perception at the edge, feel free to reach out, and I'm happy to answer any questions. Thank you.
Thank you very much. And I think those three presentations, whilst covering roughly the same topic, have had quite dramatically different areas of solution. I'm now going to ask Christina for the final presentation before we go into the Q&A session. I would ask people to use the Q&A window. We have one question there at the moment, but use the Q&A to pose questions for the final session of the day. Christina.
Yes. Hello, can you see my screen?
Yes, everything looks fine.
Perfect. Okay. Good afternoon also from my side. My name is Christina Schwarz. I am a software developer for engine controls in AVL. And today I am presenting some use cases for using reinforcement learning on the edge in engine controls. I'm going to talk about specific challenges that the automotive industry is currently facing in software development and the motivation for using AI-based algorithms for engine control. Then I'm going to introduce you to the strategies for air puff controls and diesel particulate filter controls using reinforcement learning and why it is important to execute the AI techniques on the edge. Finally, I would like to summarize the advantages and disadvantages of using AI in engine controls. So what are the main challenges that we are currently facing in the software development for combustion engines? First of all, we have the legislative push for emission limits becoming harder to adhere to every year. To meet the targets, both software and hardware development is essential. Second, the same software should be applicable to a high variation of vehicles, such as passenger cars, commercial vehicles, and even construction vehicles. And third, the software should be applicable worldwide and should consider different ambient and weather conditions, traffic conditions, and other realistic variations in the operating environment. These challenges lead to a very complex software structure and an extremely high calibration effort, which is very cost intensive. This is why in the past 25 years, the software and controls have changed completely and have gained huge prominence. The complexity of the functions in engine control units has increased immensely, while on the other hand, the vehicle development time has decreased. Also in future, it is not expected for the software complexity to decrease, especially if we consider changes in the user behavior and steady advances towards the market adoption of autonomous driving or connected vehicles. With the usage of artificial intelligence, we can increase the calibration efficiency, which translates to a considerable cost reduction. Furthermore, we can apply the machine learning models on several different vehicle types, which enables software portability between a wide range of vehicles. And finally, by employing data intelligence, there is a potential to achieve huge improvements in terms of model training, as more environmental and operational information from various global locations can be exploited for model training. Now let's consider the air puff control. AVL's experience with air puff controls started almost 20 years ago. In 2005, we were able to build the first testbed demonstrator using our software. The results were validated in a vehicle later on, and several SOP projects followed, where we extended and improved our control algorithms year by year. To get an overview of the air puff, I'm going to touch upon the main components and their influences. There are two key variables that the air puff control relies on. These are the lambda, which is the air-to-fuel ratio, and the intake manifold boost pressure. The lambda is controlled via the exhaust gas recirculation valve, also called EGR valve, and the intake throttle. And the intake pressure is controlled via the turbocharger. Now, the problem is that the actuators have a strong influences on the sensor values. This is indicated with the blue arrows in the figure. The trade-off between performance and robustness is conflicting crosswise in the coupled MIMO system. By replacing the standard controllers with a data-driven model, it is possible to achieve improvements in model accuracy as more environmental conditions are considered for the model training. Furthermore, the usage of these data-driven models is significantly reduces the calibration effort and therefore leads to a cost reduction. Additionally, we could use the data-driven model to detect an air mass drift for a lambda adaptation. As the inputs to the data-driven models change rapidly, a high flow of information is required, and the execution of the AI algorithm on the edge is indispensable. The second application, which I am presenting today, is the data-driven temperature control of the diesel oxidation catalyst to burn the soot in a diesel particulate filter. Here on this slide on the top left, you can see a state-of-the-art after-treatment system for Euro 6 applications. Euro 6 is the current emission legislation standard. The system consists of a diesel oxidation catalyst, also known as DOC, the diesel particulate filter, DPF, and the NOx reduction device selective catalytic reaction catalyst called SCR. The diesel particulate filter uses a wide range of applications to filter out particulate matter such as soot and ash from the system. When a filter gets full, for control engineering, when the accumulated soot comes to a critical point, an active regeneration is triggered to burn the soot. To do so, temperatures of up to 600 degrees Celsius are necessary. In a normal operation, such high temperatures are not generated by the combustion engine. Therefore, the fuel is oxidized, so burned in the diesel oxidation catalyst in order to heat up the system. The amount of fuel which is needed for the temperature increase is calculated normally with a closed loop controller, whereas the dead time is a specific challenge. Our strategy is based on replacing the standard controller with a data-driven model to reduce calibration efforts and therefore again drive down the costs during the vehicle development phase. Furthermore, the data-driven approach enables the inclusion of wider operating conditions for improved adaptability to different ambient conditions. This is especially important when considering the aging behavior of components. Again, the relevant input signals to the data-driven model can be very transient and need to be updated in real time. This is why also for this use case, the computation on the edge is essential. After explaining some of our use cases, I will now sum up the advantages of using AI-based algorithms, but also highlight some drawbacks. But first, let's recap why we would like to use AI-based algorithms in the automotive sector. The ever so more stringent emission legislation is imposing on the software to have a higher precision in controls. The time to the market is getting smaller and smaller, and development costs need to be reduced. And at last, by incorporating AI-based algorithms, a reduction of energy consumption can be achieved due to lower computing efforts. Finally, I would like to provide an overview of the advantages and disadvantages we see in using these algorithms. First, the advantages. There is a significantly lower computational effort when executing new control algorithms on an automotive controller in comparison to the standard approach. Furthermore, the radical change in the development process can drastically reduce engineering efforts. However, drawbacks also need to be considered. First, a lack of transparency of machine-learned algorithms reduces the ability to analyze the model in details, as it is the case with a physical model. Second, the new engineering skills are required. And third, due to the nature of machine learning algorithms, huge amounts of data are needed for training purposes. However, from AVL's perspective, the future of automotive controls relies on the usage of machine learning, especially with the execution of AI algorithms on the edge. We see a big benefit for our future applications. That was all from my side. Thank you.
Thank you very much. That's very interesting, and I think brings us back to the fact that the car has many systems in addition to self-driving. What I'm going to do now is ask the presenters to put the videos on, and we'll go into the panel session. We have had a couple of questions posed, but by all means, any of the delegates use the Q&A window to pose additional questions. Let me start with one of the last questions posed, which was, Christina, you mentioned new engineering skills, and I guess that's applicable to all the areas. What sort of things are we looking at? Christina, do you want to pick up on that?
Yes, so especially in engine controls, we are used to just use MATLAB Simulink and normal programming for these engine control units. And here our technical field is not yet very used to these neural networks and to AI algorithms for really the engine control, like throttle valves and so on. So there, for at least in AVL, we need to build up more knowledge about these topics.
And Cyprian, from a Infineon's viewpoint, do you find changes in the needs of your customers in terms of moving from engineers to people who perhaps more IT related?
Generally, this move is observable, yeah. While I think it differentiates quite a lot across the different business lines. For example, if you look at automotive, this is, from my perception, a slower moving business in this sense. The whole value chain is quite established, and I think the people sense, and it also happens already, that changes need to happen, but it's rather slower than I observed it in my former employment, which was with mobile systems, means mobile systems of handsets, which has a much higher dynamic. Yeah? But in general, this trend has to be coped with, and I definitely see the need that this is moving forward. As I said, in automotive, I would say the customers are rather not yet asking so explicitly for the expertise. Yeah?
Okay, and Prof. Crossu, obviously your talk started with very much biologically inspired systems, something that engineers wouldn't necessarily come across. How do you see our ability to include some of these wider experiences?
Let's point out first that actually neural networks were originally inspired by biology too. It's only that the idea was that they were inspired by spiking neurons because most of our neurons are spiking. The only problem with this is that the activation functions used in deep neural networks nowadays, they are not spiking. Okay, so they are really smooth. And this model that was originally developed for artificial neural networks for a single neuron is not correct from a biophysical point of view. Now, when you connect the neurons together, you get to a model that is closer to, let's say, a biological model. but it's still a conductance model. I mean, like I showed, actually what happens is that you have currents passing through the membrane of a neuron. Now, I think every electrical engineer would be able to understand a capacitor model. I think almost every participant here has looked once in his life at a capacitor equation. So this actually builds a link between, let's say, deep neural networks, which are in fact analog, and this biological model that I've shown. Now, they are very similar in the, with the single difference that we have an additional gating component which makes currents out of. So it's not, the rate of change of the membrane potential is not the sum of conductances, it's the sum of currents, like we all know from physics and from electrical engineering. So, but it has advantages in terms of what it can express. So what you learn with them, and we use the same tools as everybody else. We use TensorFlow, Keras TensorFlow. So we can apply exactly the same tools to do machine learning. The only difference is that our resulting networks are much smaller and much more robust to noise. Because the capacitor itself, if you remember from electrical engineering, is a filter. It's a low-pass filter and a high-pass filter, depending how you set it up. So it automatically filters noise, similarly like what happens in our brain. So I think that in this respect, I don't think there is a problem from engineers to get into AI, because they're going to see their equations that they were accustomed to. And I think that we are now seeing a convergence also between control theory and machine learning, because much of what we are doing with reinforcement learning, this was called optimal control before. Supervised learning is called system identification in engineering. And so I think that there is a very nice convergence that takes place that is happening now. And we have to teach the students these things and let them work with the tools from machine learning. And I think we are on a good path for the future.
Thank you. And Garion, are you seeing a wider community being used to prepare the roadmaps that now we're not only using engineers with a high degree of knowledge of car and automotive systems, but now requiring the skills from ICT people who really understand the AI components, but don't understand what a car does?
It's exactly this. I think the nice thing about the partnerships that are being prepared for Horizon Europe is that they're quite strategic, and strategic in the sense of combining technical knowledge with non-technical knowledge, with user expectations and so on. And all of a sudden, this can no longer be served by just bringing in your engineering knowledge out of a small segment of the technology spectrum, but you need comprehensive solutions from the start then. Just consider those examples as we have seen them in the presentations, or that I tried to show, with humans and machines interacting. And I believe it's very clear that therefore, that part of knowledge needs to be included, and it's really difficult to distinguish the importance and the roles of just little breaks out of that.
Okay. And Elizabeth, just a comment from you about membership of EPoSS. Are you seeing more ICT companies or different companies joining EPoSS compared to the traditional membership?
Sorry, I was muted. Actually, we are working on that, and this is also the idea with initiating these kind of webinars and working together, because our board has identified how important AI at the edge is for the EPoSS community, and so they told me to really move in this direction. And of course, we are welcoming people bringing in these opportunities. We have, as you've seen around the table, Infineon, AVL, being members of EPoSS since long time and being already part of this. But I think it is an area, a growing area of interest for our members, and an area where we should connect also with companies not yet being members. So warm welcome to everybody who is interested in this kind of collaboration.
Thank you. And Simon, within the KTN, do you think we're seeing more cross-sector work than we had traditionally done within individual sectors?
Yeah, I think there's a definite drive towards it because people are starting to struggle inside their own fields, especially having worked with the transport team at KTN on things like the connected autonomous vehicle work with embedded systems. It feels like people are having to bring multi-talented teams together to cover different aspects, most definitely.
Thank you. Obviously you're building a new company and coming from an ICT background potentially. Do you find that you have to include engineers that understand car systems, or because of the areas you work, it is primarily software type skills and AI?
That's a really interesting question, actually. So I think from our team, the main expertise is in computer vision, image processing, deep learning. Some of our team come from medical image processing background, or from a pure maybe robotic or deep learning. So it's really, I think our team's expertise is really on the AI side. So there's definitely learning in terms of the automotive transportation market, learning about the pain points, etc. Where I find working with partners and collaborators really, really helpful for that aspect. So I think from our team is really coming from a technical perspective. How do we address some of the technical solutions, and sort of acquiring other skills as well? So it's really a mix. But it's definitely quite interesting. So that's why when we are onboarding new members, usually we would give them a task that's looking at processing some automotive related data. But a lot of them haven't come from that background, but was able to, with the background information to deliver what we need technically. And there's usually we would have a lot of sessions on looking at industry development, etc. So acquiring the industry insight through our own research, but I think most importantly through collaboration with partners and customers in this field. Okay,
and Alfred, I'm going to continue with you because we've seen within the context of a car, we see that the power requirements for the AI systems, the GPUs, etc., are quite significant. Maybe new technologies are helping develop that down. But when we come on to other areas such as drones, can you ever conceive some of these systems being power efficient enough to put within a drone?
Yeah, absolutely. So some of sorry, I'll let you finish this.
No, it's going. Yeah, how hard are we pushing the power budgets these days? Is it going to require something really dramatic to get low power?
I think with a drone application, with the payload and with the battery capacity, I think power is even more important there as well for, say, autonomous operation. While we primarily focus on automotive and transportation, I think one of the key things is, can we add more functionalities to some of our customers, their existing computing platform, especially when they already have a system, say buses or in a public transport space. I think that's where that would really make a big difference in that sense, because it's a difference between AI and no AI at all using the same system, and it can really for them to add a lot of value. So I think that's kind of where we focus on as well. It's to enable application that wouldn't have been possible if it wasn't for algorithm that's able to run on extremely power efficient computing platforms.
Okay. And Cyprian, you obviously focused on both the power budget and the data budgets that come in from these. Do you ever look at very low power stuff, the sort of things that would be applicable to drone type systems?
Yeah, to a certain extent, especially the project which I showed has the target to find solutions to this, and I think as I showed also in the presentation, it is crucial to find solutions here which enable us to cope with these complexities which we are facing, because it's not a solution to run with 1 kilowatt compute power in the trunk when you want to reach a certain range with your electric car, yeah, at the end. And here I would say, at least to the experience which we gained so far through the project, I would see a little bit different with the skills which you need, by the way, for addressing these topics. Talking about spiking neural networks, here the coding of the information is already a challenge in itself. So if we start doing a processing in an asynchronous and analog fashion with these networks, we have to deal with completely different codes and encodings as we would do with these classical artificial neural networks. Yeah? It's not a vector matrix operation. It's temporal contrast encodings and stuff like that, which you have to look at. And sometimes it's really taking a completely different viewpoint to the problems. And I think this is a skill which needs to be substantially developed. This is something which is not that present, and also you find rarely in the education, because these networks were primarily driven through the biological motivation and mimic the biological behavior, explaining it. But when we're now looking at the industrial usage, it's all about these encodings, the learning algorithms for it, and they are quite different to the classical artificial neural networks as we know it. Yeah?
Okay, and obviously, Radu, your presentation was showing ways of doing quite dramatic reduction in power. Do you think that will continue with ever more power efficient systems?
Yeah, absolutely. I think the key to understanding what we are doing relies in having expressive solutions that lead to very small networks that are easily explainable. Now, let me point out that in my view, this analog computation that I showed, you can think of it as the part of machine learning, and you can think of it as the firing rate of spiking neurons. So if you want to put this in a low power system, you have to implement everything with spiking neurons. I mean, there is no other way. But my view is that spikes are really an efficient analog to digital conversion. You convert the amplitude of a signal to a spike train, which is easy to reinforce. It's pretty much like digital transmission. Neurons do this at the beginning of the axon, and at the end of the axon, they convert it back to concentration of neurotransmitters. So from the point of view of learning, what the neurons see is really something that is totally analog. But you cannot reliably transmit the information from A to B if you don't do spiking. So that's where the advantage, I mean, no matter what implementation of machine learning you want to do that is power efficient, like our brain, for example, which is amazingly power efficient, you have to do this analog to digital conversion. So these two things, you can decouple the learning component from the implementation part. You know, from the point of view of learning, it's enough for you to know that you have a spiking rate, and that gives you an amplitude, and there you can do the machine learning. But if you want to run this efficiently, we have to develop this, and I'm very happy that Infineon is doing this, you know, because this is, even in chips, you cannot reliably transmit information of even on small distances because of noise. So you have to do spiking. I mean, that's why the life found out that they need to have spiking neurons if you have to propagate on large distances. Now in the retina, which is only 0.5 millimeter thick, the neurons are not spiking, and there are billions of them. You know, everything in the retina, which is has 6 layers of neurons, happens in analog. But that information to be transmitted to the brain, you know, to further processing, is done with spikes. So these two things coexist actually.
It's interesting because we had thought we may do a webinar on really advanced implementations, looking at in-memory processing, all sorts of things as part of the AI, trying to predict what will happen in 10, 15 years. Gary, and just broadening it out, obviously today we have done a focus on connected autonomous vehicles. Are we missing other applications for AI within the car? That what we're looking at is the sexy new stuff of being able to go to work whilst reading a book in the back seat. But in fact, the autonomous systems and the AI, as Christina demonstrated, in things like fuel economy, engine control, the driver sort of safety systems, Is that an area that we should have focused on, and is that an area where you see great developments?
Actually, I think it's both. Of course, in the first place, it's applications in automation connectivity seem to be a little bit more sexy, right? So it's like, as you're saying, you immediately can imagine situations where you sit in the back of the car and you're playing things and you're reading a book or whatever instead of driving, whereas the applications in the powertrain you probably will not see. Yeah. But on the other hand, I think it's a very exciting application field too. It's probably something that's a bit less driven by customer demand rather than by regulation, for example. Just consider that we all need to justify in Europe our actions, activities, our proposals for topics against a Green Deal. And if we want to do that, we absolutely have to consider these as well. And I believe that there's still far more, but of course, powertrain and control is the most obvious ones. But if you go beyond that and leave the car and just consider, all the situations we are in a mobility system, how, for example, streams of people and paths of people are maybe controlled and steered and proposed, anticipated in a city. There's a huge area where it could play an important role too.
Okay. And one question, Christina, do you have a comment in that you're working down in the actual systems within a car? Do you ever feel you'd love to do more on the self-driving vehicles?
On the self-driving vehicles, we at ABL, we also trying to get a foot in, and but also for just for the powertrain controls itself. The application of AI is relatively recently employed in our company due to the gained experience that on the neural networks and on the AI technologies. And it is very likely that we discover new areas for improvement on that also in the powertrain control.
That just a personal comment. That's very interesting. Within the UK, we've got a big program on electric drivetrains. Well, really power electronics, where it has been around motors, it's been around the power electronic side. But one of the things that is becoming clear is that the controls in those areas are much less known. So I may come back and ask you to talk on something else. A final question that we probably can't miss out, which is ethics and predictability on AI. Let's start with Gerin. Do you see that that is going to be the real stumbling block for self-driving vehicles? Do you hit a child or a bleacher beat?
I believe I understand the point. This has to do a lot with awareness, right? So people, of course, need to understand how an AI system would react and would decide compared to a classical system, in order to better get and maybe better accept something that might otherwise be a little bit unsure or maybe frightening. The important thing that also engineers need to understand is that an AI system is a system that needs to be trained, and that of course needs to be tested in order to understand how it will react. And that's a complete change of paradigm. And it's also something that, again, in the technical community, people need to be a little bit more aware of at first, and then it is something that also users need to understand and need to be made aware of, that maybe the technical system might be behaving like a person that's learning something from scratch.
And Cyprian, a difficult question, I'm sure. Where does responsibility lie? With the supplier of the technology, the person who programs it, or the person who sells the vehicle, or the driver?
As of today, with the ADAS systems, I lost your audio.
sorry, I spoke. It is, yeah, just how do you control who has responsibility in these areas?
One short answer would be not at all. Yeah. But the point is that the reason is for ADAS systems, there's the clear definition that the driver still is in charge up to level 3, and level 4 and 5 are the ones which are getting autonomous. Yeah. And here we have to find also different models. I would say in the first place, it's definitely a kind of not yet really fully clarified setup, who's responsible and who takes responsible. I would give here just my very individual view on this, and I would say what we mostly have to work on is and have to hardly work on, I think, is this perception of how these solutions are, the perception of these solutions is. Because if you imagine there's an autonomous driving vehicle which is causing a deadly accident, and then compare it to a human driver, and if we look then at the statistics, let's say you have deployed autonomous driving in a large scale, and you can prove that the amount of deadly accidents is 10% of that what we had beforehand, with human drivers. Nevertheless, I think there will be a huge debate about that. With this autonomous car, or a vehicle which was causing these deadly accidents. As I said, from a kind of individual viewpoint to this, in the first place, a lot of that should be actually covered by a reasonable setup with the insurance settings, because there's certainly an ethic discussion, but if you can prove that you come down with to 10% of the former accidents, from a certain point of view, it doesn't matter who is causing the accident, you have less, and it's actually an improvement. But it's quite obvious that there still will be the discussion about the moral component of this, because it's a machine and not a human which was causing that. But if you take a very let's say fact-based or statistic-based view onto this, actually it should be, as long as it is sufficiently well addressed by concepts for the insurance, being addressed. But as I said, I think this is one thing which is still to be discussed in great detail, and we are not yet there.
Thank you very much. It was a difficult question. We're at time, but I was going to just ask one last question to each of the presenters, which is about the future, the bits we accept, we don't know. Where do you think we'll be in 10 years' time? And is there anything that would really surprise us? Radu, start with you. Where will we be in 10 years?
Yeah, I think we are going to see these spiking neurons. I mean, control is going to merge. Control theory, computer science, and machine learning, artificial intelligence are going to join forces. It's more or less the same field. I very much hope that people were shy before to get into nonlinear controllers. So that was the big difference in control theory. People were identifying linear systems. Now we go in nonlinear systems. So my hope is that the systems that we are going to synthesize in the future are going to be understandable, much more understandable, partially, if you like, maybe designed, and only what is not totally unknown is going to be learned, but what is known should be out there. Like in convolutional neural networks, there is an architecture, and that's why they are so, which was inspired by biology, the receptive fields. So I think we are going to have much more explainable models. We are going to have huge data sets, which are going to be able to solve some problems in ethics, because we are going to ask our machines to do exactly what the people do, and if we give them training data, they can learn that, and we are not going to be surprised what these machines are going to do. And yeah, it's going to be a lot of automation. Our systems, it's going to take still a long time to get to the amazing abilities of the real neurons. So we are still going to be the smarter ones. So there is still hope for us.
Thank you. How do you see 10 years' time?
I think Radu covers it really well, like in a very comprehensive way. I think what I would hope to see is also the use case and the application of computer vision deep learning becoming even more prevalent than today, and further contributing to autonomous systems, and also an increase in terms of the human trust in those systems, how we work together alongside with them, and really allowing them to contribute to productivity, efficiency, and well-beings of human beings. So that's really what I hope to see, and what we wish to see too.
And Christina, how do you see your world in 10 years?
Yeah, hopefully AI on the edge will be an essential part of the safety critical components also in engine controls, and will help us to to keep the emission legislation limits, to keep them and to get the world a little bit nicer.
Thank you. And Cyprian.
Yeah, a lot was said already. I want to just comment a little bit more pessimistic, because usually one tends to have a colorful picture of the future. And this is based on my history, because I was first in contact in the 2000s, early 2000s, with spiking neural networks, doing simulations on that, and seeing now after 20 years what's happened and or not happened. So, but anyway, I also hope to see that we have parts of this as a solution in autonomous driving cars in 10 years. Yeah, there are companies out there which are claiming that we are earlier with autonomous driving. I guess we can be lucky to see it in 10 years.
And Garion, coming to you, I'm afraid I came to you last on the grounds that you do lots of work on roadmaps, and therefore you know what we're doing in 10 years' time. How would you see it?
Sure, I won't tell you. No, Nigel, I believe, I still believe that mobility is an area where, as I said, all people are experts, everybody can tell about it. And therefore it's so prominent on the agendas. But at the same time, we do see a lot of potential of transfer into other application fields. And I think that's the big opportunity that we have, and that we see applications in health, or that we see applications in city development and so on. And I'm a bit more optimistic. Maybe I have the hope that it will make technology in everyday life a little bit more wise. And so I'm thinking of maybe we turn smart mobility and smart cities into wise mobility and wise cities, and that definitely needs a lot of AI.
Well, it's always nice to end a webinar on a positive note. So with that, I would like to bring this session to a close. We will issue a feedback form. Please do fill that in and just give us some comments. There is the Meeting Mojo sessions running all this afternoon. So if you want to connect to other people, please do go on there and find out who the other delegates are. And I'd encourage you all to try and connect. So our next webinar will be in early December. I have in fact got 1 or 2 slots still open. So if anyone is actually working on AI implementations in healthcare, particularly interested in instrumentation there, so bringing it down towards how medical instruments are improving with embedded AI. But thank you very much to all the speakers and the organizers. It has been a pleasure working with you all for this time. And thank you very much for those delegates that are still with us. I hope you've enjoyed it. Use the feedback form to tell us how excellent it was, which is the preferable answer, or what we need to improve. Thank you very much, everyone. I'll now ask Natasha to close the session.
Thank you very much for inviting us.
Thank you, Nigel.
No.